Smart City Seminar hosted by Texas Supercomputer Center. Dr. Wei Jiaxu and I co-hosted this event. So today it's our great honor to invite Dr. Lei Kang from Uber Eats to give us talk about their method to predict the demand and their how to do prediction at Uber level. Dr. Kang received a Bachelor of Transportation Engineering degree from Tongji University, then Master degree from also from Transportation Engineering from Purdue University. Then his PhD from UC Berkeley in Transportation Engineering, also a Master in Biostatistics. He's currently data science tech lead manager at Uber. So welcome, Dr. Kang. The floor is yours. You can start.
Cool. Yeah, thanks for the introduction. Let me share my screen. I think this one. All right, can you guys see my screen?
Yes.
Okay, cool. I think that's guys started. Good morning, everybody. Thanks for having me here today. My name is Lei. I'm a applied scientist at Uber, working on Uber Eats Marketplace. Very excited to share with you some of our work in time predictions on behalf of our team. So for the sake of time, I will not go into the modeling details, but rather providing a very high-level description about the applications. So the work presented here is a joint effort among data scientists, applied scientists, engineers, products across multiple teams at Uber. So I want to thank all of them for their contribution. A little bit of context about Uber Eats. Uber Eats is the largest food delivery platform in the world outside China. It provides fast and reliable services to our customers by connecting merchants and delivery partners in a very efficient way. For example, if you open Uber Eats app, we will provide a variety of selections, including like restaurants, grocery stores, alcohol, pharmacy, convenience store, etc. Especially during COVID, the online ordering platform like Uber Eats has played a very critical role in fulfilling customers' needs while helping the local economy to survive and thrive again. Uber Eats has started around 2016, and since then, it has grown super fast from a few pilot cities to a global markets, including US, Canada, EMEA, APAC, LATAM. So just for illustration purposes, I only include the growth map in 2016, but we are still in a very fast growing mode right now. Currently, we are operating over like 6,000 cities right now. And here's a visualization for some of orders that were placed across the globe. Hopefully that gives you a sense of the scale and the magnitude we are dealing with. Okay, so for today, I would love to give you a very general overview about Uber Eats Marketplace, and then dive deep into, I prepared two problems I want to discuss, but I think for the sake of time, probably I'll go deeper into one problem, namely the meal prep time. And but if you guys are interested, you can like shoot me an email later. We can have some follow-up sessions afterwards. Okay, so marketplace prediction. Uber Eats is a three-sided marketplace. So the goal of the marketplace team is to connect those three sides in the most efficient way. In the marketplace, we have pricing, including customer pricing, delivery partner pricing. We also have dispatch, batching, demand shaping, etc. Time predictions are used to empower all of them. For example, as a customer, you place an order either through a web or a mobile app. Then we need to predict a delivery time and communicate that value to the customer in order to set a proper expectation about when the food is going to be delivered. After the restaurant accepts the order, we also need to predict how long it will take the restaurant to cook the food, because the dispatch system is going to use that prep time prediction to find the right delivery partner to arrive on time when the food is ready. And for each delivery partner, we also need to estimate this dispatch offer, we send to them. We need to predict how long will it take them to finish the delivery, which includes the travel time on the road, parking time, waypoint time at a restaurant, waypoint time at a drop-off location, etc. And those trip time predictions will be used by the pricing to calculate a fair payout for the delivery partner. So as you can see here, accurate time predictions will help the platform achieve the optimal decisions in terms of making trade-offs. Let me give you one example about the trade-off we are facing. For example, we're talking about meal prep time. Why that's important? Because meal prep time affects dispatch timing, like when should we dispatch a delivery partner to pick up the food? So the high-level objective of dispatch timing is to find a delivery partner who can arrive on time when the food is ready, so that there's no time being wasted. However, if we overestimate meal prep time, then the dispatch system is gonna dispatch a delivery partner later, which means the food will need to wait for the delivery partner. Meanwhile, customers also need to wait longer. However, in this case, the waiting time of a delivery partner at a restaurant will be shorter, because by the time he or she arrives at the restaurant, the food is very likely to be ready. Right? Makes sense? So or vice versa, right? If we underestimate meal prep time, then what will happen is that very likely a delivery partner needs to wait longer at the restaurant. However, in that case, the customer's wait time will be shorter, because whenever food is ready, we have a delivery partner waiting there to pick up the food right away and make the delivery. So basically, there's a trade-off between delivery partner's waiting time and the customer's waiting time. And the meal prep time plays a very critical role in improving this kind of trade-off. Cool. Do you have any questions at this point?
So please turn off your audio, audience, to allow Dr. Kang have a proper presentation. Thank you.
But yeah, also feel free to stop me if you have any questions. I think we should have time, enough time to go really deep in the prep time prediction. Okay, so let's dive deeper. So here's a graphical view of a life cycle of an order, right? So from the moment you place the order, we estimate how long will it take for the restaurant to cook the food. And then we find a delivery partner accordingly, and which means we need to calculate what's the travel time, what's the parking time. And then we, on a high level, we're trying to match this travel time with food ready time. So by the time the delivery partner arrives, the food is ready. That's the high level goal. Then the delivery partner make the delivery, travel to the customer. We also have this end-to-end prediction to show the delivery customer how long they are expected to receive the food. We call it estimated time of delivery, or short for ETD. Okay, so let's start with the meal prep time prediction, which are used by dispatch to empower all the dispatch decisions. So this is a restaurant view about meal prep time prediction. So on the restaurant side, they have a tablet, and which shows them how many orders are there and what's their prep time. We show those prep time prediction to the restaurant in order to set a better pickup time expectation. And the restaurant can adjust our original prediction accordingly based on their indoor operation, their staffing capabilities. Currently, we are using SG Boost models to make predictions. But what makes prep time prediction interesting? It's just like a very typical supervised learning problem, right? So what makes it difficult? So here are three major challenges we're facing. The first one is noisy labels. We do know the ground truth about when the food is ready. For example, merchants, they are supposed to press the food ready button on the tablet whenever food is ready. So in this case, in the tablet, there's a button you can press. However, in reality, the usage of that button is very low, because when they are super busy, the restaurant, they don't have bandwidth to interact a lot with our tablet. Furthermore, some restaurants or some merchants, they like to game the system by pressing that button, even if the food was not ready, because they prefer to have a delivery person waiting at a store so that they can ensure the food is hot or fresh. Now the question is, how should we enforce the true prep time? Without this good learning target, our machine learning model will not do a very good job, right? The second challenge we're facing here is very complicated order details. Different cuisine types and the meal types like Chinese food, Indian food, Italian food, their prep time will vary a lot. If you have a fusion restaurant, then you can order like Japanese food and French food at the same time. How should we make a prediction for this kind of combinations, right? That's also very challenging. Moreover, an order may consist of a combination of different items or SKUs. Those items also interact with each other. For example, I have one order consists of like 2 burgers and 3 fries, versus another one consists of like 3 pizzas versus and 2 Cokes. Both of them have 5 items, but their prep time will differ a lot. So how should we make predictions for that? The next one we have here is the business. How busy a restaurant is at the time when the order is placed is also super important, because restaurant characteristics and the staffing also affect the meal prep time processes. So, but we have our limited information about how busy a restaurant is. We know how many orders there are from Uber Eats platform, but we don't know how many customers out there in the store, how many others coming from other platforms. So how should we capture those business? So let me share with you some of our thoughts on the solutions to address those problems. So the first one is how to denoise the ground truth labels. Here we're using Delivery Partner's mobile data to try to validate the restaurant signals. I'll go back to this later. The next one is leverage the dish descriptions, and how can we use models like the neural net to learn interactions or embeddings to better represent this kind of combinations, right? The next one is we have access to rich Uber rides data. Can we use Uber rides data to sort of inform how busy that area is, so that we can use that kind of information to inform restaurant business? So I'll go over those challenges one by one. Challenge one is noisy labels. And we have restaurant signals, as I said before. We also have the Delivery Partners explicit signals. So upon arrival, Delivery Partners, they can, in their app, they can press a button telling us whether food is ready or not. But again, in reality, not all the Delivery Partners will give us such information. So we have to be a little bit clever or smart in terms of using other explicit signals to validate the signals we have been collected. And one intuition here is, if a Delivery Partner has to wait a very long time at a restaurant, then that's an indication of food was not ready. Then very likely we're gonna trust our Delivery Partner signal versus whatever restaurant signals prior to us. So the question is, how do we define long waiting at restaurant? If the problem is, how should we define the start of the arrival versus the start of the departure? One possibility is use GPS signal. We can, based on GPS signal, we can tell, okay, how far away this Delivery Partner is from the restaurant. But the GPS signal is very noisy, and in a lot of places, the error or precision of GPS is not that super reliable. So that's why we have to come to this mobile data from the Delivery Partners. So here's our high-level idea, right? So we have those GPS data from our Delivery Partner. We have the mobile sensor data. We have the activity recognition data. And what we can do is, can we build a model to predict which state this Delivery Partner is at, right? For a given trip, there could be driving, there could be like a waiting at a restaurant, there could be trying to find parking, there could be like a walking, right? So different states we can predict. And using those data, we have built using a conditional random field model to build this trip state model, which for each trip we can label what kind of state they are in, are they driving or they're waiting. To be more precise, what we have done so far is we ask human labelers or operators to label different trips according to the labels we have. And so now we have our labels, we have our like input features like GPS, motion data, the speed, activity recognition. Then we can predict which state they're at for a given trip. Then with this model, we can apply it to other more broader unlabeled trips. And what we get is for each trip, we have this kind of predicted labels. And this is done in an offline fashion. Now with this predicted labels, what we can do is, we can define parking because those labels help us tease out or decompose a trip into different states that allow us to define, okay, what's a parking time this different partner spend at a restaurant or at a utility location, right? This can help us build a parking prediction model. The second use case, which is probably more interesting to us, is we can decompose the waiting time from their time spent at a restaurant neighborhood. And those waiting time, if they wait very long time, that's indication of food was not ready. So we use that signal to validate the whatever signal the restaurant provided to us, so that we can denoise the ground truth labels. So that's our application. In terms of like a parking inference, one thing we can do is we have the labels from this predicted from the predicted. So we have the parking prediction from those like predicted labels using the conditional random field model, and then we apply to other trips. And for each trip, we have this kind of inferred parking time. Then what we can do is we can build another model to predict this inferred parking time, so that we can get a sort of parking time prediction. So one example here is by using this model, we can decompose the distribution of this trip into like how much time they spend on waiting, how much time they spend on walking, how much time they spend on trying to find the parking. So that's our like solution for the first challenge. But I want to pause here to see whether there's any questions so far. Okay, now let's move to the second challenge we're facing, the very complicated order details and also this kind of item level interaction. How should we model that? So we are exploring representation learning based on these descriptions to learn embeddings that allow us to better capture order details. So here's an embedding graph that we have learned so far. It shows promising directions to separate out different cuisine types. But another thing you can see here is there's also exists a large variability among orders. And this is an area that we haven't explored very well yet, which highlights exists huge opportunity for us to improve. But just want to give you a rough sense about the improvement we can get. So here are some results where we're using very simple multi-layer perceptron and compare that with the SGBoost model in production. Where with this very simple model, we're able to achieve like 4% error reduction. And this is the area we are actively exploring, which is how to use like deep neural net to better represent the dish types or the item types, so that we can better capture all their interactions. So regarding the next challenge, the restaurant business, right? As I mentioned, we have access to Uber rice data, which tell us how many trips are generated from an area and how many trips are going to an area at a particular time of day. Then what we can do is, can we do some sort of aggregation to map those restaurants with those areas to infer their business? Suppose we know for this kind of time period, a lot of trips are going to that particular region, and there's a restaurant in that region, then very likely that restaurant gonna become busier than before. So this will become a signal that allow us to infer the restaurant business. And this is also another area we're exploring where we can better leverage the Uber rice data. But before I move to the delivery time prediction where we show to the customer, I also want to pause here to see whether any questions before I wrap up the meal prep time prediction.
Could you say what the What's the value to you in understanding the item interactions and the types of dishes that you had as challenge 2?
Sorry, what do you mean by that?
Like, why do you need to know? Why do you need to understand what type of food it is, or what the different items are? Like, what value is that in this three-legged, in your business model, or in the service that you're providing?
Right.
Why does it help you to understand what type of food it is?
Right, because our goal is trying to make the most accurate prep time prediction so that dispatch can use that. Right. If our prep time prediction is not accurate, I think I mentioned that before. If we underestimate or overestimate, which is going to result in either courier waiting at the restaurant or the customer waiting for the food.
So I see. And so the assumption is that the type of food, the type of food is strongly correlated with how long it takes to prepare it.
Exactly, like Chinese food versus like Indian food, their prep time are very different, and also different restaurant, according to their staffing. They're even for the same restaurant, if the staffing are different, the prep time also differ a lot. So how should we capture restaurant signals, and how should we capture especially for the item itself? That's also very challenging and also very important to us, because we want to accurately predict how long would it take for this restaurant at this moment to cook this food.
I see. Thanks.
Cool. Anything else before we move on? I think I only have 6 minutes, so I will very quickly go over the delivery time prediction. So as a customer, you open the Uber Eats app, we'll show you various informations, right? Which one important information is the time. Because as a customer, whenever I open the app, I'm pretty hungry. I want to have my food to arrive as soon as possible. So in that sense, the original time promise we make with the customer is super important. And in this case, actually, we show two type of values. One is what we call eyeball ETD. ETD stands for estimated time of delivery. Eyeball ETD, we show a range, because that's before they place any order, they are shopping around different restaurants. And this kind of like eyeball ETD will help them decide, do I want to order from this restaurant or not? Then after they place an order, we show a post-order ETD, which contains more accurate information about the order. Because after they place the order, we know all the order details. We know how many items in the order. We know the cuisine type, the meal type they placed. So we can have a better estimation about the time. But that's also the expectation we set with them. That's why having accurate time is very important, because it decides whether they want to place the order or not, and during the eyeball stage. B, from the post-order perspective, if our order are super late, it's gonna hurt the trust we build with them. It's gonna hurt the long-term retention. They may not come back to us again, right? So that's why having an accurate delivery time prediction or ETD prediction is super critical to us. However, this is also a very challenging problem, because there's an uncertain marketplace. At the time when we make the prediction, we don't know whether we have enough delivery partners nearby. We don't know which delivery partner we're gonna dispatch to. We don't know whether they're gonna accept the order or not. We don't know whether this restaurant, they're gonna take a longer time than we predicted to cook the food. We don't know the traffic condition in the future, right? For instance, this order may take 40 minutes, but the traffic may become really bad after 40 minutes between the customer and the restaurant. So how should we incorporate all those information, all those uncertainties into our prediction? And also there's like city level heterogeneity, different restaurant level heterogeneity, right? Different restaurant, they have different like preparation process. So all those like uncertainties add as additional like complexity on top of our predictions. I'll skip this one. So very simple approach is, can we just add up different components together? Can we add up the travel time, add up our predicted meal prep time together? The answer is that's not the good approach. The reason is there are so many moving pieces that we cannot control for. For instance, we need to forecast like how many trips will be played, how many trips will happen in this region, how many, what's the availability of the given partners, are they going to accept order or not, this kind of acceptance prediction, and also the like meal prep time prediction, the travel time prediction, all those moving pieces, which we don't know yet. Also, by the time when we need to make a prediction, we don't know whether this will be a car or this will be a biker, right? So the biker or car drivers, their ETA will also be super different. So what should we do there? So our approach is to combine all those information together and stacking all those different model inputs to generate the final model output. And having this kind of end-to-end approach, we're able to make more accurate predictions because those like individual model inputs already account for those information that we have. So this kind of end-to-end approach so far has given us the best performance. We're also actively exploring neural network models like deep learnings. How can we learn the representation of the restaurant? For instance, like we're in current production, we're using XG Boost model, but we know XG Boost is not very good for those high dimension categorical features, right? How can we represent a restaurant fixed effect, restaurant embeddings? So that's why we're looking for those kind of neural net models so that we can have a more powerful algorithms to generate the most accurate predictions. I just want to like quickly wrap up here. I think today we discussed some of the application we have so far, but I don't have enough time to go to all those modeling details. But if you have like, if you are interested in our problem space, shoot me an email. I'd love to like connect with you so that we can have more discussion later on. We're always hiring. If you are graduating or have interest in our team, please shoot me an email. We're opening for like San Francisco, Seattle, and New York office. Okay, that's from my side. Do you have any questions so far?
I have a quick question. So as a person who uses Uber a lot, Uber Eats and subscribing Uber One as well,
yeah, great.
I'm curious about how grading system hurts the prediction modeling. And the second one is
I'm sorry, for the first one,
if you look at the Uber Eats, we have this grading system, right?
Rating system.
Like rating star.
Oh, rating system.
5 or 5. Yeah. So I'm curious about how does grading system kind of hurt the model's performances. And the second one was how does delivery prediction handles the noise that sometimes the foods are wrong delivered, right? It doesn't really have. I really experienced that too, but I'm curious about how those noises are handled in delivery predictions as well.
So I think for the second one, we do remove those outliers from our training data. I think that helps reduce the noisiness introduced by those outliers. Hmm. And for the ratings, so first of all, we're not using any ratings in our predictions. We are just using the marketplace condition. And also for instance, the nearby courier supplies. Do we have enough supply of the couriers? The restaurant historical performance, right? For this restaurant, historically, how long would it take for them to cook the food? And also the real-time traffic condition. We have those information, but we are not using rating per se in our prediction models. We don't want to penalize our customers in a very unfair way.
So there is no big difference between 3-rated restaurant and 5-rated restaurant in terms of prediction, right?
So I think the restaurant will be different, right? Their restaurant characteristics, like how long will they take in general, historically, will differ. But we do not have a feature telling us, okay, this is a 3-star restaurant versus 5-star restaurant. But their historical performance will tell us the difference, right? If this restaurant historically had been cook food very fast, then their like prep time will be faster. So we have more reliable predictions also for the customers.
Okay, thank you.
Lei, I have a question for the delivery partners. How many hour average they work? I'm talking about the vehicle best and how much money they make daily or monthly.
That's a good question. Actually, I don't know. Yeah, I'm not best person to answer that, to be honest.
Okay, and
But yeah, I think it depends. Some there are some like sort of like full-time, quote unquote full-time delivery partners who do this a lot. I also like use my sparse time to make deliveries, to do deliveries. So, but I work like maybe like 2 hours per week, something like that. So it varies a lot.
so what's the payout structure for the delivery partner? We know you have a tip and you have a cost. What's the split between Uber delivery partner and basically Uber and the delivery partners?
So regarding payout, we have a real-time incentive. We also have like a basic pay. Beyond that, as you mentioned, there's also tip. And in terms of the distribution of, okay, what's the percentage come from base pay, what's the percentage from tips, it varies by cities, and also vary by the customer. I would say, I live in New York City, and I receive a lot of tips. I think the people here are very generous about giving tips.
So the tip you received will 100% go to the delivery partners, not go to Uber, right?
Yeah,
That's
yeah,
Uber
absolutely, yes, yeah, 100%.
Another question, we know Uber had price search functions. So in the busy time, they were guiding people to the high demand areas. So how the price search function play out in this estimate delivery time? Will you consider the potential supply after you raise the delivery cost to downtown region?
Yes, I think that's a really good question. So first of all, from the delivery partner perspective, we do have this search map. We show, so when they open the app, we show a map where there are like a lot of orders about hot areas. So we do have that for the partner. From our like ETD prediction, we have our supply demand forecasting information, and that's got a replenished every like 5 minutes. So every 5 minutes, we refresh our like features, and that is used in the prediction. So that's in like a real-time updates.
Okay, thank you. I think we are at the time, and we can have one more question, or if audience has question. Otherwise, we can wrap up here. So, do we have other questions? So, if no questions, thank you, Dr. Kang, for a wonderful talk today, and Dr. Kang, if you can stay a couple minutes after the talk, that'd be good. So otherwise, the seminar is finished. I will see you after 2 weeks. Bye, everyone.
Thank you.
Thank you. Thanks, folks.
那个
Hey, are we still recording?
Okay, let's close this.